theorems, the fun stuff. Some of these are junior cert, some of these you would have done quite a bit of work with at junior cert, looked at formal proofs of, and others you might have just done questions with. But we're going to recap all of them because they are important and they do inform how we tackle geometric problems going forward. So, theorem language. We saw in the syllabus there's a couple of words and a couple of theorems that we need to work with. So here's some of the examples. A theorem is a rule that has been proved by following a list of steps known as a proof. So we talked about something that didn't need any formal proof, and we just took it as that's the job, that's true, and that was an axiom. A theorem is in a way is like the opposite of an axiom. This is something that does require proof. A corollary is a statement that follows directly on from a proof previous. Now, what that means is I have done this proof and I've proven this idea to be true, and because of that, here's another little idea that's now true. Okay, so it's not a completely new idea, it's connected to the proof just before it. And I suppose something I should say is quite important. When you look at these theorems, they have to be done in order. Why I say that is you cannot use something from Theorem 10 to help you with Theorem 2 or 3. It's just, we decided for our geometry system that that's just not the way we're going to work. So you have to, and you won't get marks for this, you have to take the theorems in order, and you can only use earlier theorems to help you with ones in the future. Okay, and that's where the kind of corollary idea helps, because a theorem gives you a corollary. So without the theorem, the corollary wouldn't exist. Okay, for example, there is a theorem that talks about each angle in a semicircle being 90 degrees. And I'm going to show you later on what theorem that stems from. Converse then is another one. The converse of a theorem is almost like the reverse. Okay, and I'm going to show you what that looks like now in a second. Okay, so the converse. When we talk about a converse, what's quite helpful to do is split a theorem up. Now, I've taken a non-mathematical theorem, and that's just to kind of help us with the understanding. But you break a theorem up into two sections, A and B, an if and a then, right? So if something, then something else, okay? So if the statement is if A, then B, so whatever A is, then the converse of that is I swap A and B. So I leave the if and the then exactly where they are, and I just swap A and B. So converse would be if B, then A. So let's have a look, right? I tell you what, we'll color code these and I'll match them up with the sentences below, and that should give us a better understanding. So we'll put the B in green and the A in yellow, okay? So for example, if a man was born in Dublin, then he is Irish. So my if is the man being born in Dublin, then he is Irish. That's my B, okay? So then, if I want the converse of this, so that's my statement, S. If I want the converse of this, I'm essentially swapping the yellow and the orange, yellow and the green. If a man is Irish, so if a man is Irish, then he was born in Dublin. Okay, so a couple of things here. You can see that swap. Okay, so that's what I was talking about. The converse is essentially you take the two sort of objects of the statement and you switch their order. That's why we kind of think of it like the reverse. So, the reason we want to talk about this, if a man was born in Dublin, then he is Irish. Makes sense, yeah? Now, here's an issue with the converse. Sometimes the converse may or may not be true, but the original statement can be. It doesn't always have to reflect the original statement. So for example, if the statement, this is the statement, that's true. If a man was born in Dublin, then he is Irish. Okay, makes total sense. Now, if I swap them around, is that true? If a man is Irish, then he was born in Dublin. No, it's not. He could be born in any other of the counties in Ireland. So, the converse here is not true, but the statement is. And that's perfectly okay. The converse does not have to reflect the statement. Okay, okay, let's have a look at this idea of formal proof. So, mathematical proofs usually follow the following headings. Right? Now, these are becoming less and less important. So if any of you have any friends or siblings that are going to be doing their junior cert from this year on, they don't have to do this anymore. Okay, this sort of strict learning off proofs. The general sort of flow is the same as it always has been, but just we don't have to have these strict headings, but they're still helpful to know. Okay, so typically the headings we have are theorem, so you say what theorem it is that you're trying to look at. Given, so what are we given? What's the information I'm given or starting out with? What do I have to prove? So what is the specific thing I need to prove is true? Do I need to do any constructions? Do I need to draw in something here to help build this together? And then finally, proof. What are the sort of mathematical steps to link all this together? Now, you saw a little bit of this back in the construction of root 2 and root 3. Okay, similar ideas. So let's have a go. Something similar. So here's an example. I've kind of populated some of the ideas. The theorem we're trying to prove is that the angles in a triangle all add to 180 degrees. Okay, that's what we're trying to do. And a triangle with angles A, B, and C is what we're given. That's what we're starting with. What I'm trying to prove is that if I add the angle A, the angle B, and the angle C, I get 180 degrees. Here's a construction. So there's my diagram that I'm starting with. And for this one, the construction is drawing, not with a highlighter though. So let's just get rid of that. So for this one, the construction is drawing in a line that is parallel to BC that goes through A. Okay, and the idea here is in the formal proof, you look at the values of these angles and show how that this is a straight angle. And there, that's the same as that, that's the same as that. Okay, and then we do that with our triangle, prove all these angles, add up to 180, and that would be the proof part. Again, not going to spend too much time on that, but that's the general idea.